Last but not the least, the final talk of the session from Jan about post-quantum XML and SAML, single sign-on.
Okay, so thanks for coming to my talk. My name is Jan Opitsky, and this is a joint work with Johannes Miller on the topic of post-quantum XML and SAML single sign-on. So it's a lot of loaded titles, so let's parse through it. So let me first briefly talk about XML. If you don't know, XML is a markup language used for data serialization, but a lot of security protocols are XML-based, primarily SAML, which I'm going to be talking about later. There is also like this HL7, which is a framework of protocols that are used by healthcare providers to talk to each other. And there is also this SADIS, which is a IDAS compliant electronic signature standard. So it's accepted in EU as an electronic signature standard. If you want to do XML, if you want to do some security in XML, you have basically two building blocks, which is XML signatures and XML encryption. And those are like, there are two separate standards for that. So SAML is an XML-based security framework to exchange information. So it's a set of protocols that kind of have a similar message structure, and they use the messages are XML documents. But the main kind of use case for SAML is to implement a single sign-on scheme. Compared to like consumer-based single sign-on schemes, which are mainly based on like JSON-based OpenID, SAML is heavily used in industry and academia. For example, my university uses it, my old university used it. In Luxembourg, we use it to log into our banks or to our governmental like to do your taxes, to see your healthcare receipts and stuff like that. Yeah, so it's heavily, every identity and access management typically supports SAML. And there is also this one prominent implementation, open source, is Shibboleth, which is also used by this In Common Federation, which is a federation of US universities. So you may have heard about it. So how does a single sign-on SAML protocol works? It's very simple. So basically the user wants to log in at the service provider. So we have three participants. We have the service provider, the SP, the user, and the IDP, the identity provider. So the user wants to log in at the SP. He says, yeah, I want to log in. The SP creates a authentication request, which is a SAML message. The user will forward that to the IDP, and the IDP will process this request and begin an authentication. This is kind of out of scope of the SAML protocol. It can be like multi-factor authentication, it can be a passkey, it doesn't matter. But after the IDP completes the authentication, he will issue a response which says, okay, I have authenticated this user, or it failed, and I certify that I did it. And this response gets forwarded back through the user to the SP. He will process the response and potentially issue like a authenticated authorization cookie to the user. From a security perspective, the authentication request can be optionally signed. Like the standard doesn't require it to be signed, but the response has to be signed because otherwise the user could forge his own responses and log in, impersonate any user. And there is also optional XML encryption if the IDP wants to send some secret information to the SP that just the standard supports it. So what's post-quantum? What's the problem? The SAML and XML standards, because they are very old, all standards currently support only classical cryptography, where what I mean classical cryptography is basically all crypto that's based on the hardness of factorization or discrete algorithms. Unfortunately, Peter Shor in 1994 came up with a quantum algorithm that solves this problem in polynomial time. The good thing is that it's a quantum algorithm, so you need a big quantum computer to run it, so I hope nobody has it yet. But the development is like continually increasing, so better safe than sorry, and let's be prepared for that. Yeah, and the obvious threats are, you can forge signatures. For example, in SAML, you can impersonate any user and you can authenticate as admin and steal private data or something like that. For public encryption, you can decrypt it. And what's kind of also important that you can already begin collecting the encrypted data now and store it. And then when you get a quantum computer, you can crack it later. So that's kind of called the store now, decrypt later strategy. So it may be already happening. So to the rescue comes post-quantum cryptography. Post-quantum algorithms is basically the name for every algorithm that's resistant to the Shor algorithm. They are typically based on hard problems in lattices, codes, hashes, multivariate equations for isogenies. The main venue where the standardization or development of post-quantum algorithms happens is due to NIST that had this standardization process since 2016. Initially, there have been 60 submissions, but 2 years ago they announced 3 finalists, which is they selected 3 signatures, and 1 key encapsulation mechanism, which is basically something like public encryption. You can look at it, and they are supposed to announce another key encapsulation mechanism that's probably going to be a code-based, some code-based algorithm. So the algorithms are already developed. The trend now in post-quantum crypto is also to kind of hybridize it, which is, what does it mean? Is to combine classical algorithms with post-quantum algorithms. And it has this, the hybrid post-quantum solutions have the property that as long as one of the algorithms is secure, the whole system is secure. The motivation is that you want kind of the best of both worlds, which is the maturity of classical algorithms and the quantum resistance of post-quantum algorithms. And it's been kind of recently motivated because a lot of post-quantum algorithms have been cracked after 20 years and 10 years of thought to be secure. So the trust in them is kind of not ideal. And it also, hybrids provide kind of compliance with existing regulations, because they say, okay, you have to use classical crypto, but you want to also use post-quantum crypto. So you can use both, and you will the compliance officers will be happy. But the problem with hybrid solutions that there is no general blueprint how to do it. For every protocol, you kind of need to have a specific solutions. So our contributions, we have looked at, so we design post-quantum solutions for XML signatures, XML public encryption, and consequently kind of we get post-quantum SAML. For everything, we provide a purely post-quantum solution, which is kind of a non-hybrid, which uses only post-quantum algorithms, and we provide a hybrid solution. We provide a implementation, proof of concept implementation with Java. Due to that, we had to fork these multiple libraries, which is OpenSAML, Apache Santuario, and Bouncy Castle, which is the JavaScript, open source JavaScript library. And we provide performance experiments of we tested our solutions, how does it perform. So let me briefly go over the one solution. So for post-quantum signatures, the purely post-quantum signatures are kind of easy to do, because the standard is kind of what we call crypto agile. We just switch out the signature for a signature. There is not really much to do. But if you want to hybridize it, it's kind of more challenging. So we propose 2 solutions, which one we call composite signatures, and the other one what we call separate signatures. And the main difference is kind of that the separate signatures are what we call backward compatible. And what does it mean? We say that hybrid signature is a backward compatible if it can be verified by a classical only party, which is like a real world example. If you are an IDP, you want to issue post-quantum secure responses, but you have some clients that haven't upgraded their system, so you want to support all of your clients, and you don't want to deal with any problems with that. So after you get post-quantum XML signatures and public encryption, you basically get post-quantum SAML with some caveats, and because of these multiple solutions, you can kind of configure your SAML how you want. You can get purely or hybrid post-quantum, or backward or non-backward compatible, and you also have to kind of in the end select the primitives. So this is an example of one test that we did. This is the hybrid solution of a non-backward compatible SAML. It's we kind of simulated what happens when the SAML protocol runs. So there is a lot of signature verification, encryption. But one interesting thing is kind of post-quantum algorithms are kind of pretty competitive with classical ones. They have the high bandwidth requirements, but basically compared to RSA, they are way faster, for example, than RSA, because the lattice algorithms are very fast. So there is not much overhead if you want to do post-quantum crypto. So in conclusion, we provide a foundation for securing XML-based protocols against quantum threat. We provide a proof of concept implementation with fork libraries, which can be kind of used to either migrate your SAML system or other XML-based protocols. It can get inspired. We provide the code. It's linked in the paper or on the program in the artifacts. we did like performance benchmarks, and we also in the standards we kind of identified a few places where the standards need to be updated because frankly the standards are pretty old, so and very complex. So yeah, so that's it, and thank you for listening and answer questions.
We already have our first question.
Thank you very much for the talk, very interesting. I have one question in terms of if you actually want to deploy SAML, you also have dependencies on secure channels. So you need to have a TLS implementation or something like that, either unilaterally or mutually authenticated. Do you have future plans to create post-quantum secure channels as well?
Yeah, I mean, that's kind of, I skipped because I didn't have time. So like for TLS provides kind of a secure channel between the user agent and the SP, and the secure channel between the IDP and the user. So it's kind of complementary to the signatures, complementary to SAML. There are already existing solutions for post-quantum TLS. I don't know if you know, already in Google, if you have Google Chrome and connecting to Google servers, you are already using like hybrid key exchange. You don't have like the authentication, but they have already deployed it with cooperation with Cloudflare. So like post-quantum TLS is kind of a solved problem. I also have a paper like survey of post-quantum TLS, so you can kind of find it. And yeah, so ideally you would be, if you want to say post-quantum SAML, you would be using post-quantum TLS in combination with this, so they would kind of complement each other.
Any other questions from the audience?
Yeah. So about the forks you publish on post-quantum SAML, are there then plans or anything to merge them with the main library?
So for the composite signatures, that's a kind of they are kind of separate from the SAML and XML. I just implemented it because I wanted to test this solution, and that's already in Bouncy, so it got accepted. This is based on like an IETF standard. It was a draft, now it's a standard, I think. So you can already use it, for example, to like create a certificate with composite hybrid signatures. So that's already in the standards. And for the other ones, I'm planning to reach out or make a pull request, but I haven't gotten around to it because there is also I want to make something better. So, but I haven't had the time to. But I plan to contact the maintainers and cooperate with them to do it.
Okay, thanks.
We can take one more quick question, if it's quick. There's a question online.
Yep.
Please go ahead.
Can you hear me?
Yes.
Great. So the backwards compatible, how does that work with like store and decrypt later, right?
Yeah.
Like if they don't understand the quantum now, they can't decrypt it now, and if they can decrypt it now, then it can be stored and decrypted later.
Yeah, good question. So that's kind of a caveat I skipped over. Yeah, you can do backward compatibility makes sense for signatures, but it doesn't make sense for encryption because there is no it doesn't make sense. So so for you cannot have you cannot have like a backward compatible SAML which uses hybrid encryption. But also in SAML, like the signatures are kind of the I would say the main security mechanism and the core of SAML. The encryption is kind of an additional, and you can also use kind of some basically you are right.
So if I'm understanding what backwards compatible signatures gives you is that if an SP has not upgraded, then they're secure as long as no one has a quantum computer in their back pocket today.
Exactly.
And if they did upgrade, then they're secure even if someone has a quantum computer in their back pocket today.
Yes. So it's if you haven't upgraded to post quantum, obviously you don't know anything about post quantum, so you are not secured. But it's kind of a compatibility compromise that like at least you get the classical stuff until you upgrade, and it's kind of the usability and migration. It helps with this migration. I think that like the IDP can just issue these responses. It's compatible with the standards. That's kind of what it means. That it doesn't. The response is like standardized, so it doesn't. The person that hasn't upgraded is not surprised that this message has kind of some kind of unknown things that I can process. So yeah, you are right. Yes.
Thanks.
Okay, let's thank the speaker again, and one round of applause for everyone.